Ever wondered what keeps modern cities standing tall, cars rolling, and bridges spanning rivers? The answer is steel, strong, versatile, and essential in nearly every aspect of our lives. But steel doesn't appear magically in construction sites or factories. It starts as raw iron ore and undergoes a carefully controlled high-temperature journey before emerging as the sheets, beams, and rods that shape our world. Let's take a full step-by-step look inside a steel factory and explore mass steel production from start to finish. Raw materials, the building blocks of steel. Steel production begins with raw materials, each chosen for its specific role. The most critical ingredient is iron ore, usually in the form of hematite Fe2O3 or magnetite Fe3O4. Iron ore is rich in iron, but contains impurities such as silica, sulfur, and phosphorus. Removing these impurities is a crucial part of the steelmaking process, as leftover contaminants can make the steel brittle or weak. Other essential materials include coking coal, used to make coke, a nearly pure form of carbon that fuels the blast furnace and aids in the chemical reduction of iron. Limestone serves as a flux to bind with impurities and form slag, which floats on molten iron and is later removed. Scrap steel, recycled steel, is often added to the process, improving efficiency and sustainability. Before production begins, each material undergoes quality checks. Iron ore is analyzed for iron content and contaminant levels, while coal is tested for its carbon content and burning characteristics. Even small variations in these raw materials can affect the final steel's quality, so precision at this stage is essential. Coke production, fueling the furnace. Coking coal must be converted into coke, a crucial step in steel production. Coal is heated in large coke ovens at temperatures exceeding 1,000 degrees C, 1,832 degrees Celsius in an oxygen-free environment. This process removes moisture and volatile compounds, leaving a porous, carbon-rich substance. Coke serves two critical functions in the blast furnace. Fuel. It burns at high temperatures, generating the heat necessary to melt iron ore. Reducing agent. Carbon from coke reacts with iron oxides in the ore to produce molten iron. The quality of coke directly impacts furnace efficiency. Strong, durable coke supports the heavy layers of raw materials in the furnace and ensures uniform airflow, which is vital for producing high-quality iron. Blast furnace, turning ore into pig iron. The blast furnace is the core of traditional steel production. This enormous vertical structure can be over 30 meters tall and operates continuously, 24/7. Iron ore, coke, and limestone are carefully layered inside the furnace. Then, a blast of hot air, sometimes over 1,200 degrees, 2,192 degrees, is injected at the bottom. Inside the furnace, reduction, carbon from coke reacts with oxygen in iron ore, converting it into molten iron. Fluxing, limestone binds with impurities like silica to form slag. Separation, molten iron, called pig iron, collects at the bottom, while slag floats to the top for removal. Pig iron contains a high carbon content around 4 to 5% and is brittle, meaning it cannot be used directly. Its carbon level must be reduced before it can become ductile, workable steel. Basic oxygen furnace BOF, refining iron into steel. To transform pig iron into steel, it undergoes refining in a basic oxygen furnace BOF. Molten pig iron is poured into the furnace, sometimes mixed with scrap steel to optimize energy usage and composition. Then, a high-speed stream of pure oxygen is blown into the molten metal. This process oxidizes excess carbon and removes impurities such as sulfur and phosphorus, which are converted into slag and skimmed off. Within about 20-40 minutes, the carbon content is reduced to the desired level, between 0.02% and 2%, depending on the steel grade required. The BOF process is incredibly efficient, allowing massive steel plants to produce hundreds of tons of steel every hour while maintaining precise control over composition. Secondary steel making, precision control. Even after the primary refining in the BOF, molten steel often requires further adjustment in secondary steel making. This stage fine-tunes chemical composition and improves properties. Common techniques include ladle metallurgy. Molten steel is stirred, heated, and treated with specific alloying elements to achieve desired characteristics. Vacuum degassing removes dissolved gases such as hydrogen and nitrogen, which can cause bubbles or cracks. Alloying. Elements such as nickel, chromium, or vanadium are added to produce stainless steel, high-strength steel, or other specialized grades. Secondary steelmaking allows factories to produce a wide variety of steels for construction, automotive, appliances, and machinery, each with unique properties like hardness, corrosion resistance, and flexibility. Continuous casting, solidifying the steel. Once the molten steel is ready, it must be turned into solid forms. This is done using continuous casting. Molten steel flows from the furnace into a water-cooled copper mold, which shapes it into semi-finished products, slabs, blooms, or billets. As the steel moves along the caster, it solidifies while being carefully cooled. Continuous casting is faster, more energy efficient, and produces steel with fewer internal defects than traditional ingot casting. The semi-finished products are then ready for the next stage, shaping. Rolling, transforming steel into usable shapes. The semi-finished steel is heated in reheating furnaces and then sent to rolling mills. Rolling reduces steel into the desired thickness and shape. Hot rolling. Steel is rolled at high temperatures, making it malleable and easier to shape. This produces plates, sheets, rails, and structural beams. Cold rolling. Steel is rolled at room temperature to achieve a smoother finish, tighter tolerances, and increased strength. Cold rolled steel is often used in automotive panels, appliances, and precision machinery. Modern rolling mills are highly automated, producing long sheets or coils with exact dimensions, ready for industrial use. Finishing, enhancing steel properties. After rolling, steel undergoes various finishing treatments depending on its intended use. Pickling removes surface oxides and scales formed during hot rolling. Coating, galvanizing or painting improves corrosion resistance. Heat treatment, annealing, quenching, or tempering modifies mechanical properties for strength, hardness, or flexibility. Cutting and coiling. Steel is cut to size or wound into coils for easy transport and storage. Some steel products also receive special coatings or alloying treatments to meet the demands of aerospace, automotive, or construction applications. Quality control, ensuring strength and safety. Quality control occurs at multiple stages of production. Steel samples are tested for chemical composition, tensile and yield strength, hardness, surface defects, automated sensors, and human inspectors work together to ensure that every batch meets stringent standards. A single defect in steel can compromise bridges, skyscrapers, or machinery, so accuracy and precision are critical. Recycling, a circular process. Steel is one of the most recycled materials in the world. Scrap steel collected from old cars, appliances, and factory waste is often added to furnaces. Recycling reduces energy consumption, raw material usage, and carbon emissions, making modern steel production more sustainable. Many plants integrate recycled steel directly in the BOF or use electric arc furnaces (EAF), which rely primarily on scrap, further increasing efficiency and reducing environmental impact. Step 11. Shipping, from factory to industry. Once processed, steel is cut, packaged, and shipped to construction sites, manufacturing plants, or distributors. Steel comes in various forms: sheets, coils, beams, rods, and pipes, ready to be incorporated into buildings, vehicles, appliances, or industrial machinery. Logistics are carefully planned to minimize handling damage and ensure that steel reaches its destination efficiently. Because steel is heavy, transportation involves specialized trucks, rail cars, or ships. Step 12. Sustainability and modern innovations. Modern steel production focuses heavily on sustainability. Energy efficiency, heat recovery, and advanced furnace designs reduce fuel consumption. Alternative fuels. Some plants use natural gas, biomass, or hydrogen to reduce CO2 emissions. Carbon capture. Emerging technologies aim to capture and store carbon emissions from blast furnaces. Innovation is critical as the steel industry balances growing global demand with environmental responsibility. Conclusion. For from ore to everyday life. The journey from iron ore to finished steel is a remarkable process of chemistry, physics, and industrial engineering. Each step, coke production, blast furnace, refining, casting, rolling, and finishing, is meticulously controlled to produce steel that is strong, durable, and versatile. Every building, bridge, car, and appliance you encounter depends on this incredible process. Steel's combination of strength, flexibility, and recyclability makes it the backbone of modern infrastructure. So next time you walk across a bridge, ride in a car, or admire a skyscraper, remember the long, fiery journey that steel takes, from raw ore through furnace flames to the versatile material that shapes our world. If you enjoyed this deep dive into steel production, don't forget to like, subscribe, and comment on what industrial process you'd like to explore next.